All right, AP Biology, it's time for a nice cool glass of properties of water. Because water is the most important molecule to life. All right, so the first thing we need to talk about is sort of where we left off with the chemistry presentation, is this idea that water is a polar molecule. Basically what happens is water is a covalently bonded molecule. You've got two hydrogens, which you can see right here and here, and you've got the oxygen, which is right here. Now what happens is there are 6 electrons from the oxygen, and there is 1 electron from each hydrogen. So what this does is this creates a cloud that has 8 total electrons. The hydrogens feel like they have a full valence shell. The oxygen feels like it has a full valence shell. But the thing is, the hydrogens right here have 1 proton each. And this oxygen has 8 protons. And protons have a positive charge. So you've got a 8 size positive charge versus a 1 size and a 1 size. And then you've got this 8 size negative charge that goes through the whole thing, but it's going to spend more of its time here over the oxygen nucleus because the connection between these two charges is bigger. What that does is that creates a situation where the electron cloud spends most of its time near oxygen, so the oxygen side of a water molecule has a slightly negative charge. We call that a partial negative charge. And the hydrogen sides of a water molecule have a slightly positive charge. Think about it. The hydrogen nuclei are not strong enough to attract the cloud. So the cloud, which is negative, spends most of its time near the oxygen. That means the hydrogen nuclei are more exposed to the environment, so they have a slightly positive charge, because in the nuclei is where the positive charge can be found. So water is polar because the oxygen contains a slightly negative charge and the hydrogen contains a slightly positive charge. Now this charge is weaker than the charge that forms between ionic compounds, but it does form a slight bond that we call a hydrogen bond. You can see in this diagram right down here, this symbol means partial, so you got partial positive and you got partial negative. Well, just like in ionic bonds, opposites attract, and so you get to form a slight bond here, and we call that a hydrogen bond. Now we've mentioned these before, they're actually what holds DNA together. But what they come from is the partial positive charge of polar molecules. Individually, hydrogen bonds are absurdly weak. Like they're very weak, much weaker than ionic bonds. But as a group, they could be a powerful force that causes many effects in nature. Okay? And because of this polarity and because of this hydrogen bonding, all right, these are the underlying causes. Water has some unique properties that actually end up making it ridiculously important to all living things. The first of these properties is known as adhesion and cohesion. Basically what it boils down to is water is polar. And if it's polar, it has a slight charge. If it has a slight charge, that means it's attracted to things of the opposite charge. That means water is attracted to itself. Water is attracted to certain charged things like glass, other ions. And the great example is cellular structures in trees. This creates a bunch of interesting effects. First off, over here, you see the combination of adhesion and cohesion together and what they can do. Adhesion is the molecules of water's charge attracting to the inside of certain cells, as you can see here, water conducting cells inside tree trunks. And then here you can see their attraction to each other, to themselves, creating this almost chain. Well, when water is attracted to itself, we call that cohesion. When water is attracted to other charged things, we call that adhesion. Well, the combination of cohesion and adhesion is actually what drives water from the roots to the top of the tree. Transpiration, which is water evaporating from the underside of leaves, pulls the water up. Well, the reason the water gets up there is because the adhesion allows it to connect to the inside of the water conducting cells, and the cohesion allows it to connect to each other so it holds on to each other. All right? And that actually literally is all that gets water up to the top of a tree. And as you should know, trees can be quite tall. Also, a great example of cohesion in effect is the top of water. There's actually a lizard that's commonly called the Jesus lizard because it walks on water, because it uses the idea that water molecules on the top of a body of water are cohesive with each other, and so we can run across the water if it moves quick enough. Incidentally, that's why it hurts when you belly flop. All right. Think about when you get out of the shower in the morning. Water beads on the surface of your skin because your skin is not a charged surface, so water coheres with itself. All right. Easy example why this is important is many living systems, like the whole tree situation, where how it uses this property to get water from the roots to the top. But it is something that you encounter rather frequently, and living systems make good use of it. Next up on our hit list of properties is water's high specific heat and high heat of vaporization. So let's talk about this. Before we get into this, we have to talk a little bit about what temperature means. When you're like, oh, it's 50 degrees Fahrenheit out, that means something. It's like, yeah, it's cold. Yeah, it's hot. But what does it mean? Well, temperature, depending on the unit, Fahrenheit, Celsius, Kelvin, is actually the measure of the average kinetic energy of the molecules in the system. Okay? What you have to understand is molecules are constantly in motion. Constantly in motion. And temperature is sort of a measure of how fast they're moving, because it generates, if there's enough heat, the molecules have more energy and they move quicker. Okay? Well, water is kind of cool because it has a very high specific heat, which is the amount of energy that a substance is able to absorb and release. Okay? So you could take a look over here. You have like specific heat. All right. Let's just take a look at the example of concrete. Concrete has a specific heat capacity that's measured in 800 joules per kilogram degree Celsius. Water, 4,200. Significant difference. Think about this in terms of a hot summer day. You go outside in a swimming pool or the ocean, and you put your foot in it, and it's, you know, maybe lukewarm. That's it. All right. But you go outside and you step on asphalt, concrete, the street when it's like 90 out, you're going to burn your skin. And that's because concrete has a much lower specific heat than water. And what specific heat is it's a substance's ability to sort of resist temperature change. It can absorb energy before it increases the rate of movement in the molecules. And that specific heat is because of the hydrogen bonds. They help water absorb more energy. They keep the molecules moving at a lower rate. What this also does is when it gets cold out, all that energy that's in the water that it absorbed gets released back into the environment, which actually keeps the environment a little bit warmer. So what happens here because of high specific heat is water is able to regulate the temperature of the environment. Think about this while you go through the winter, all right? Watch the news. Look at the temperature in the west, away from water. Like, you know, the middle of the country, the middle of the state. And then take a look at the temperature on the coast, near a body of water, like the ocean. What you'll notice is that in the winter, it's colder the farther you are away from a big body of water. And in the summer, it's hotter the farther you are away from a big body of water. Which at the surface, it doesn't seem to make any sense, but it's because of the high specific heat. Near water, when it's cold, water can release all the energy that it's stored. When it's warm, water can absorb a lot of energy before it starts to evaporate, before it starts to get really hot. And that's important for maintaining stable environments that life is able to survive and thrive in. The other one is that water has a really high heat of vaporization. And heat of vaporization is the amount of energy required to convert a substance to a gas. All right. Basically, think about it. Boiling water. All right. You want to boil water. You need to give it a certain amount of heat, and then it starts to come off as steam. Well, just like having a high specific heat, water has an absurdly high heat of vaporization. It actually, based on molecular weight, should boil at a much lower temperature, but it does not. And it does not, because not only do you have to provide enough energy to speed up those molecules so they can get away from the water and become steam, you also have to provide enough energy to break all the hydrogen bonds that are being formed and broken all the time. And so that means that water boils at a much higher temperature than it normally would. And what this does is this helps maintain an environmental temperature that is good for life. All right? If water boiled at too high of a temperature or too low of a temperature, then the overall temperature of the globe would be much lower. Life would not be able to survive as well. But because water boils at such a high temperature, the overall temperature of the globe can be much higher because there's still liquid water available. This also allows temperatures inside living organisms to be relatively high, which is good for chemical reaction functioning. High temperature, more energy, reactions happen faster. Think about it. Your internal body temperature, 98.6 degrees Celsius. All right, I'm sorry, 98.6 degrees Fahrenheit, roughly 37 degrees Celsius. That's pretty damn hot. And if water turned into steam at a much lower temperature, your body wouldn't be that hot, and your chemical reactions wouldn't happen fast enough. Last up on our list of properties of water is the idea that ice floats. Put a glass of ice. Put some ice in a glass of water. Put 1 cube. The ice will sink to the bottom and then float to the top. Do it in orange juice. Do it in milk. Do it in soda. Because all of those things are majority water, and so is ice. Interesting thing about that. Water is the only substance that does that. All right? It's the only substance who, if you take its pure, solid form and stick it in its liquid form, it doesn't sink. Molecules, elements, they all have 3 phases of nature. They are either a solid, a liquid, or a gas. And which state you are in is a representative of how quickly your molecules move. Your molecules are always moving, even if you are a solid. They just kind of vibrate back and forth. If you're a liquid, they move freely, but not that fast. And if you're a gas, they move very quickly and spread out from each other. All right? Solids tend to be very densely packed. The molecules are right on top of each other. They're very dense. The liquid, they're more spread out, which is why in most things, the solid form will sink to the bottom of the liquid form. Water's a little weird because as water solidifies, so this picture right here is liquid water. See how the molecules are all right on top of each other? Well, in a different molecule, they would organize into a crystal pattern or a structure, all right? That basically they just line up, they're right on top of each other, they get real dense and real solid, even more so than this. But this is what water actually looks like. See, hydrogen bonds are very weak. But as you start to remove energy from the system, which is what happens when something gets cold, there's nothing left to break the hydrogen bonds. So they start to become stable structures, because with no energy to break them, they exist all the time, constantly, without forming and reforming, without falling apart. And what this does is it leaves these big empty spaces between the water molecules. And that makes ice less dense than water. And that is why ice floats. Well, you may be thinking to yourself, who cares? You care. If ice did not float, all the solid water would sink to the bottom of bodies of water. The sun, which is where the earth gets its temperature from, would not penetrate deep enough into the water. And so the bottom of every ocean, every lake on this planet would be solid ice, and there'd be a thin layer of liquid on top. But since ice floats, when this iceberg here freezes way down in the ocean, because it is now less dense than the water, it floats to the top, where sunlight beams down on it and melts it, and then it becomes water again. And this whole process continues. Ice deep in the depths of the ocean freezes, floats to the top, where sunlight melts it. If that didn't happen, the majority of water on the surface of this planet would be solid, and it would be unusable by life. So there you go. Those are the properties of water and why they are important to living things.